Good morning, everyone. We're very happy to welcome some additional participants today that joined us for the Swiss Day. Some people asked us, what is the Swiss Day? Is this another national holiday? And it's actually not. What we decided is to offer the possibility to attend the Congress just for a day for people that couldn't make it for the full week, especially for local participants that are not that far away. So we have a lot of additional participants from industry, government that joined. And we hope we have a really nice international exchange today, because I think we face a lot of the same challenges and can learn from each other. Then I have just, before we start, just one small announcement. It has to do a little bit with Switzerland, the pocket knife that you received. A lot of people were worried how to take it home because they only have hand luggage. I just wanted to let you know we have a mailing service established, so just go to the information desk and you can mail it. It would be a pity if you have to hand it in at the airport. So with that, we're going to open now the next plenary debate on a very important topic throughout the world, but also in Switzerland that's hotly debated at the moment. Preserving groundwater quality for future generations. And we're really pleased to have an excellent panel. The moderator will be Peter Gradwall. He has done research on many water quality challenges over the decade and is currently Vice President for Research and Innovation at the University of Tübingen. Then we have three panelists, Juliane Holländer from EAWAG ETH said, Beth Parker from a major groundwater research center in Canada, G360, and Ilka Wallis from Flinders University in Australia. And as Peter will explain, you will have all the possibility also to participate with comment and questions. So with that, I hand over to Peter.
Thank you very much, Daniel. Welcome from my side at the Swiss Day. Basically, so you see we are a small panel, but we still have a very important topic, and we have here a QR code which will come up later, and then you can also ask questions. Before we start in our discussions, we thought to give a brief introduction of what, in our view, are the most important aspects in groundwater quality, and we all have different backgrounds here. So I would like to start, and I give you a short overview about the history of groundwater pollution, and I have to say this is my personal view, and it's maybe a little bit biased of what I did the last 30 years, and this is my take-home message in the end. So don't let them out, they won't come back again, and it gets even worse. There are more and more, and I don't want to leave it with that one. We try to work out also an optimistic view in the end. This is data I prepared some 30 years ago for a groundwater quality conference we had at that time in Tübingen, and it's about remediation timescales. And you see on the central part chlorinated solvents, benzene, toluene, xylene, and so on, and it elaborates a little bit on timescales, so it's less than years, more than 10 years, and so on. On the right-hand side, you have the PAHs, so that's strongly sorbing compounds, also PCBs and all other compounds would fall in that one. And you again see timescales we calculated, and we give a little bit of hints how to speed up removal rates and so on. And in red at the bottom, the same comes not just for solutes and sorbed compounds, but for non-aqueous phase liquids. And then you see the timescales go up. And I still remember when I wrote down here more than 1,000 years, because I didn't dare to tell the truth. Because if you have this DNAPL contamination and so on, it's easily until the next ice age, or even longer. And we know that as geologists, because petroleum reservoirs, of course, are also from the past, and they don't just vanish. So this is something we have now. And I saw some presentations here in the conference, and people in the end say, oh, it might take decades or even centuries, so this is this uncertainty. But we know it takes generations to get rid of these contaminations. So getting all kind of compounds into the groundwater is a long story. I have here the brief history of the chlorinated solvents. This is something which came up more than 50 years ago. And the chlorinated solvents, it was a great discovery of the chemists because it replaced other compounds like benzene and so on, which were used in industrial applications, and they were carcinogenic, almost explosive and so on. And so with the chlorinated compounds, one had a replacement which was really good. And the discovery continued. So since the 30s, we had the chlorinated solvents, but also the freons, for example, and then it was found out that they degrade the ozone layer and so on. And then mid of the 70s, there was a discovery, especially in the United States, that they found from chlorination of drinking water, they have haloforms. So for example, chloroform in drinking water, and at least to my knowledge, that triggered investigations also here in Switzerland, and the chemists in Dübendorf, they checked out whether they have chloroform in their tap water, and they didn't, because there was not much chlorination that was expected, but there was something else, and it was perchloroethylene. And then they asked themselves, well, where is the tap water coming from? And the answer was it comes from groundwater. And then they looked which well it was, and invisibility was a dry cleaning facility. And then it was clear, and then triggered a whole investigation also in Germany about these chlorinated solvents, basically in groundwater, but also in surface waters. And then there was further investigations, what happens to these compounds in the atmosphere, and we already had at that time the trichloroacetic acid and so on. And then people stopped using these compounds. So that was the big industry in my state in Baden-Württemberg, like Mercedes, Porsche, Bosch, and so on. And they got rid of the solvents and had other industrial processes. And I think that's a success, that people really stopped causing these contaminations. And then if you look further down, then of course it continued, and there was the Nobel Prize for Molina and Rowland, and also Paul Cruson for the degradation of the ozone layer and the end of the ozone degrading chemicals, which I think is also a success of regulations. And already at that time we looked into replacements, because the chlorinated compounds were then replaced by fluorinated compounds, and people already speculated then the fluorinated compounds also to degradation, and we could have something like trifluoroacetic acid, was already an issue then, and this is a big issue nowadays. So these old compounds come again. That was more the local contaminations, and at that time we were also aware, of course, that we have large-scale groundwater reservoirs, and this is here a fractured rock reservoir close to the city of Tübingen. And in Europe we did a great tracer experiment, I would say, on reactive transport of atrazine. So that was applied for about 30 years. And now 30 years later, after we applied it, we come back and check out what actually happens, and it's still there, and the metabolites. So it takes much longer to get these compounds out than you put them in. And I have here at the bottom a little diagram, and that shows you the red line is if you are close to the recharge area where the pesticide goes in, you see a rapid increase, and then you might see a decline. If you go further away, this is the blue line, you might still nowadays see an increase in concentration, but if you're lucky, the peak concentration will be below the input concentration and maybe below the legal threshold. And I have a little equation here which shows you that the maximum concentration of the peak to the input concentration is just a function of the times. So the exposure time, 30 years, and divided by 4 times the running time, which is now twice the exposure time. And the nice thing in these back diffusion equations is all the sorption diffusion stuff drops out, if this is the question. If you want to know where the peak is, it gets much more complicated. Okay, so with these classical contaminants, we thought we are basically managing these things and situation should improve. And now that was my last point. The new compounds come up, and this is something from Germany which was brought up in the year 2002 in North Rhine-Westphalia. And this is an agricultural plot. And they found perfluorinated compounds in tap water, in the drinking water basically, and backtraced it to this little plot. And they had a compost application, and then they put a drainage system in, what you see here in red, and a treatment plant. And we have data for these compounds now since 15 years that's still measured. And if you look in the very early times when they started to measure just two compounds, the P4 and the PFAS, you see a little bit of decline of these compounds, but then all the others, they more or less show the same trend. And if you wait 15 years, you might dare to calculate a trend from that. And this is exactly what we did. You see some surprising thing here, because these compounds, they don't behave as expected. So the short chain ones, they have very low retardation factors in KDs compared to the long chain ones. And initially we did leaching tests with the agricultural soil, and you saw the short ones get washed out in no time, and then the octanes and the decanes and so on, they take much longer. This is exactly like expected, so this is what we know. Retarded transport in groundwater shows some chromatography. These compounds don't. By no way, there's nothing, they behave all the same, they don't have any sorption differences and so on. And the reason for that is because we have precursors in that system. So actually these compounds come from something else, so there's a precursor sitting in the topsoil, this is a huge molecule, and then it decays into the side chain, and this is what we measure. And this process continues and continues and continues, and as long as this process continues, we measure, we see also the short chain ones, we see the long chain ones, and they do the same. You see some wiggles, and this is just a seasonal type of thing, and this is a hint that it's actually biodegradation which produces these problematic compounds. Okay, so this is just a little bit on the history, and with that I hand over to Juliane.
Yeah, I'm an environmental chemist, and I give now the perspective of what improved analytics help to kind of improve also groundwater quality. And here on this picture, you see already all the different contamination sources which can lead contaminants to surface and groundwater. And of course, not all more than the 100 million in the databases, not all these compounds can be found in groundwater, but there is some estimation that 350,000 chemicals are really registered for production and use worldwide. So these compounds might really end up, if they're produced in high amounts, also in groundwater. And from these compounds, on the right side, you see those which chemical abstract number, so where we know the identity, these 240,000, there are 140,000 are organics, and 75,000 are polymers, mixtures, also organics, and often not a clear identity. There are also 50,000 which we have no information, so they are kind of confidential, but we might also find them in groundwater. And of course, all these chemicals, we need to have analytics to find them. And there is quite some evolution of these capabilities over the last 50 years. So we started with gas and liquid chromatography with some unselective detectors, but then in the 90s or 1890s, mass spectrometry came into the play. We have now also LC with mass spectrometry. We have even tandem mass spectrometry, which is more selective and more sensitive. We have also ionization techniques, soft ionization, where we can really see the molecular ion, not only fragments, molecular ion, which helps us to find these compounds, to identify those which we don't know. And now also about 15 years ago, we started more and more with high resolution mass spectrometry. First more with liquid chromatography, but now also with gas chromatography, which helps us really to differentiate really molecules with very, very small, tiny differences in molecular weight. And this really give us the opportunity to see many, many compounds at the same time. And now we have also some like ion mobility. We even bring the HRMS, so the mass spectrometer, to the field. Outside of here, the conference center, you see our facility, the MS2 field, where we can go into the field with this instrument. So we have better chromatographic resolution, better ionization efficiency, we are more selective and also more sensitive, so that's why we see even more, because we can measure down to the picogram level, and also we have better data processing. So this enabled us to deal really with these thousands of peaks which we see in a chromatogram. And so this allows us to go from these legacy compounds, PAHs, to really compounds like the PFAS, which are very polar, which also can have higher molecular weight. We can also search for transformation products. So this led us to extend these target compounds, which are in 20 years ago, it were maybe 10 to 20 compounds. Now we measure 200, 500 compounds as targets. But we can also go, and because of this high resolution, we can really screen for the exact mass of compounds which we expect in groundwater sources, for example. And we can go further with these techniques. We can also try and the possibility to identify also compounds without prior information. We have not only good mass spectrometry, we have also better separation techniques. And this is especially relevant for groundwater, because for groundwater, the normally reverse phase chromatography used in liquid chromatography and also columns in GC, that does not allow us to really separate this very, very polar mobile compounds. And these are which we find in the groundwater because they are really persistent, so they don't degrade, and they are mobile, they don't sorb, as also Peter said. So, and for this we have now techniques like ion chromatography, like supercritical fluid chromatography, like hydrophilic interaction chromatography, which allow us also to detect those since a few years. Now and this is also now included into the EU, so mobility is now also there, a hazard criterium, with, I think it's very good improvement. Now I'd like to show you just two examples here from our studies within the National Monitoring Program together with the Federal Office for Environment. And here we did target, suspect, and non-target screening, and once we screened for all pesticides and all the pesticides metabolites which are in the registration dossiers. And here you see the concentration we found, and in the pesticide, the parent compounds, we found them, but often much lower concentrated than the transformation products. Sometimes we only find the transformation product. This is because the parent compounds degraded and the transformation products are sometimes more persistent than the parent compounds, and they are usually also more mobile because they're more hydrophilic. And the other thing is that we also did a non-target screening in 60 monitoring wells, which you see on the right, and we identified and quantified about 120 of 500 target compounds, already a lot of work. But then we went further and looked for all the other peaks and also assigned them based on their intensity at contaminated site, whether they are potentially also from anthropogenic sources. And about 3,000, so half of them were from anthropogenic sources. And here you see in red and blue are the agriculture and urban contaminants, which we really quantified, and then all the others are also in these groundwater sources, but we don't know yet. We just know that 50% is from anthropogenic sources and a lot is coming on from agriculture. And even sometimes we have hot spots which we only see if we do the non-target screening. And then finally, this is about better detection of many compounds, but also the time resolution can be important, especially as karst groundwater or in rivers, of course. And so therefore we have now brought the mass spectrometer to the field. So we have an automatic system which is outside the conference center, where we can really every 20 minutes take a sample and analyze it. And here you see in a creek, in blue is a rain, and in red we see then one insecticide which is coming with rain and exceeding then an acute EQS value. If we would take a composite sample of a few days, we wouldn't see this exceedance. So this helps there, and also it helps to do some source allocation, where the contaminants come from. And this you can Today, in the lunch break, there will be a guided tour to this MSD field if you are interested. And then there's also a presentation on the application for cast monitoring this afternoon. Thank you.
Okay, with that we hand over to Ika.
Thanks so much. My background is in geochemical modeling, reactive transport modeling, and I'm going to use that now to sort of switch a little bit from, we talked mainly about point source contamination so far, mainly organic contamination, so let's just zoom out now a little bit and look at more regional scale groundwater quality concerns. And I want to start with geogenic contamination. So geogenic contamination is naturally derived contamination. It is derived from water-rock interaction, and it can result in quite high dissolved concentrations of trace elements like arsenic, uranium, manganese, fluoride. And as you can see here on the figure, this is the probability of fluoride being above the drinking water guideline, and quite large areas are affected. In fact, for arsenic and fluoride alone, we expect about 10% of groundwater wells to be affected globally. This is the same figure for arsenic, probability of arsenic being above 10 micrograms per liter. So large areas are affected by geogenic contamination. The co-author of these studies is, by the way, here in the audience, Michael Berg from ERWAG, Switzerland. So if you want to know more, grab these people while you can. Switching, well, and in terms of population, so large areas can be affected, but in terms of estimates of population affected, just in terms of fluoride in groundwater, there's an estimate of about 180 million people worldwide being affected, while this goes up to 220 million, rough estimate, in terms of people affected by elevated arsenic concentrations. Switching to something different, salinity, another water quality, regional water quality issue which can affect large areas and populations. This is an example of Australia, where I'm from. So in Australia alone, less than 30% of our groundwater is actually of drinking water quality, and you can see it here in the figure. Just the blue dots, these are bores across the continent. Just the blue dots are the ones which are actually of fresh groundwater quality. The rest are all saline, and quite a few even hypersaline, so salinity is larger than seawater. Globally, salinization is mainly due to irrigated agriculture. We've got obviously a large issue also in coastal aquifers, where you may have pumping and seawater intrusion. In arid, semi-arid regions, obviously high rates of evaporation contribute to this issue. Into the future, irrigated agriculture is definitely going to increase and may increase this problem, but also coastal, salinization, coastal areas is expected to increase, just because we've got rising populations in coastal areas. So projections are for 2060 to have about 1.8 billion people living in coastal areas. Nitrate, another topic much talked about. Actually, we have talked about nitrate in groundwater since decades, and we are still talking about it. Nitrate is just due to agricultural inputs, global demand for food production, and actually nitrate is the most ubiquitous non-point source contaminant in our groundwater. I actually found, and I have to be careful here, there are so many Swiss people here, they can all correct me, but I found the monitoring network in Switzerland as an example, and so these are groundwater bores, and overall 15% of groundwater monitoring bores exceed the Swiss guideline value of 25 milligrams per liter for NO3, while that rises to over 50%, exceeding that level in agricultural areas. We are switching now to microbiological contamination. That does affect quite a lot of areas as well. Obviously, this is an issue for, when there's issues with sanitation, when people use bores which are shallow, which are potentially badly constructed, where there is a possibility for surface contamination to reach groundwater. But this can affect up to 2 billion people which consume groundwater, which may be affected by bacteria or viruses. So again, quite an important groundwater quality issue. Very briefly at the end, and I don't want to go into any detail, but I thought it is good to mention, and it sort of goes back to what the previous two speakers were talking about. There is obviously an important emerging challenge for groundwater, and that is our emerging contaminants. So these are pharmaceutical, antibiotics, microplastics, and so forth. So in the moment, this is not yet, so we start measuring these in groundwater. It's obviously still regarded as site contamination mainly. It's not on a regional scale necessarily, but it is an important emerging challenge. And I just want to mention, though, one of these emerging contaminants, because I think PFAS has managed now to go from site contaminant to a more regional threat for groundwater. We have done a lot of research into PFAS over the last 10, 15 years, and by now we do know that PFAS does even exist in our rainwater globally, and PFAS now has also been applied over much larger areas. It's not a site contamination as such anymore. Necessarily, we now know that we have applied PFAS over larger areas, for instance, through spreading of sludge. And with that, I go over.
Okay, thank you. And I hand over to Beth Parker, and we get now more into the hydrogeological perspective of such contaminations.
Good morning. Thank you for coming this morning. My perspective comes from being a physical hydrogeologist in the field of contaminant hydrogeology, and I've spent 30 years being a researcher that's involved in field studies at real contaminated sites. So just picking up from the previous discussion points here, what we've been discovering in contaminant hydrogeology is many of these contaminant plumes are late to be discovered, and they're very persistent, and therefore the variety of contaminants that Peter talked about essentially become cumulative in our water supply aquifers. So from a water supply standpoint, this is a big deal, and what's important for us to consider is which of these contaminants are more mobile and perhaps more likely to reach receptors at high concentrations or loadings versus those that might be partially attenuated over time. And then there's some types of contaminants and hydrogeologic systems where these contaminants might be completely assimilated before they reach those receptors. And so that's, I think, the evolving challenge with increasing complexity with time. So I thought I'd start with sand and gravel aquifers, and this schematic just simply is a point to say that heterogeneity prevails, even in sands. We have not only complexity or heterogeneity due to hydraulic conductivity, but we also have different scales of heterogeneity with biological and chemical reactions and the interaction between advection and diffusion. But my point here is that it requires high-resolution characterization to understand the position of these plumes, the concentration and the processes, and essentially the loading effects to the receptors. Here we have a TCE, source zone and plume, in a sandy aquifer in Florida, so it's a beach sand. And what I'm showing in the bottom right corner is essentially this plume persists amongst thin clay layers that are about 10 to 20 centimeters thick that wouldn't really get noticed in conventional characterization approaches. So high-resolution characterization identified the plume and its internal complexity, and I guess most importantly, after 40 years of source zone condition, the contaminant mass evolved from predominantly a DNAPL problem to almost entirely a dissolved and soar phase problem in the low permeability clays, even though these clays are very thin. And we wouldn't have found that out unless we were willing to take some continuous cores and sample those cores to show that the highest concentrations were stored in the low permeability zones. In essence, in the later recent decades, we can show that the contaminant mass is sourced from these clays and back diffusing out to the sandy aquifer, allowing this plume to persist, although attenuating after the source zone has essentially been mitigated. So one of the key points here is the value of core as a complementary tool to wells and multi-levels and all the other things that we've come accustomed to using. And that's because there's all these different overlapping scales of heterogeneity. And this diagram just simply emphasizes the point that we can focus on trying to clean up the source zones or stop inputting contaminants into the subsurface. But if we've been loading the aquifer over past decades, it might still take many decades for that plume to essentially flush itself out and attenuate in the system. I'd like to switch to fractured rock. And I guess the important point here is it's the fractures that dominate the flow or the transmissivity in bulk hydraulic conductivity. And just like in porous media, we can estimate the travel times knowing the effective porosity, which happens to be the fracture porosity. So we need to find ways to estimate that fracture porosity. And in sedimentary rocks, the primary porosity or matrix porosity between the fractures is an important zone where advection isn't important, but actually diffusion, absorption, and reactions can be very important. This slide is just a reminder that when we look at fractures or sea-visible fractures, not all of them are hydraulically active. And so that adds to the complexity of characterizing these systems. So here I have two-dimensional discrete fracture network realizations. They both have the same hydraulic conductivity, but the point here is the density of the fracture network influences the magnitude of diffusion and the retardation effect that diffusion is going to have on the rates of these plumes moving in the direction of groundwater flow. So a dense network of fractures on the left that TCE plume that's been evolving over 50 years in these simulations has never reached the end of that domain, which is at the scale of 5 to 1,000 meters. This is a snapshot, three-time snapshot, of a TCE plume in the Dolostone Aquifer in Guelph, the city that I live in. And so after 20 years or so of known contamination and characterization work, we started to study it in a bit more detail. But what we've been able to see from our monitoring network and kriging of the concentration data is that we have a plume that has reached its maximum extent when we first started studying it in 2003. But in 5 or 6 or 7 year increments, we've noticed that that TCE plume seems to be shrinking in volume, and concentrations are declining internal to that volume, and essentially it's collapsing onto itself and getting smaller with time. So in fractured sedimentary rock, where the bulk of the mass is in the low permeability matrix between the fractures, we might expect that these plumes never reach the receptor and may stay as enclaves within a few hundred meters from the release location. This depends, though, that we're not continuing to create more source or load that source with time. So I guess as contaminant hydrogeologists, we mostly focus on the middle scale here, which is characterizing the source zone in the plume. And I can't emphasize enough, I suppose, that it's important for us to work over multiple scales. We need to go a layer or two lower in detail so that we understand the processes and their interaction. And then most importantly as well, it really is important for us to know the flow system. How recharge is connected to discharge informs how source zones are related to plumes and receptors. And I'm not sure we're doing quite enough on the multiple scales side of things. So this diagram from the USGS has been modified here to kind of illustrate the different types of point and non-point source contaminants, and essentially that depending on where we are in the landscape, these plumes, or source zones creating these plumes, could be creating multiple plumes reaching multiple receptors, depending on how dispersed those source zones might be. And so we really need to know where our aquatards are, because aquatards will influence the refraction of these flow lines and direct those flow paths toward those receptors that we're trying to protect. So I see this as a really critical question. We're trained as hydrogeologists thinking about more transmissive zones are the focus, but we really need to understand our aquatards as well. And that brings up the primary parameter in our systems, which is hydraulic head, and how to put it to use for the greatest effect. So I'm showing here head profiles that indicate where there's head loss, and that can give us information in terms of where we have low vertical hydraulic conductivity in the system, suggesting that we have aquatard layers within that flow system condition. So now we have the challenge of wanting to do high resolution, but not everywhere. This distinguishes our objectives of characterization before we design our monitoring systems to be most cost effective. I think it's very important for us to consider high resolution characterization to do a better job of monitoring, minimizing cross connection, which can lead to cross contamination, a lot of ambiguity or confusion in our conceptual site models, leaving us not able to predict the future very well. So here we have a cartoon of the city of Guelph aquifer. It's a dolostone aquifer system. They've been using it for water supply since the 1800s. And what we now know a lot about are the various point source contaminants combined with non-point source contaminants, because we're in a very agriculturally important area in southern Ontario. And what I'm showing here too, superimposed on this cross-section, is a number of nested well clusters, so 3 or 4 monitoring wells, and complemented by nested multi-level systems. These are engineered systems that give us higher resolution data, and being able to design monitoring networks that allow us to think of things in nested scales and time and space are, I think, the future for us to consider being able to make better decision making. So my observation as a contaminant hydrogeologist over the last 40 years is that we are looking for shortcuts. And often we make these shortcuts too early in our conceptual site model development, and that's causing uncertainty that we can't necessarily quantify, but we learn it often years or decades later when we realize our predictions are off. And this leads to extra cost, and so we need to think about not just the short-term costs, but the life cycle costs and our objectives overall. But I have also come to realize, too, that physical hydrogeology seems to be getting less attention than perhaps the reactive chemical microbial aspects of contaminant hydrogeology at the moment. So in meeting our future challenges, don't forget about our aquatards. Take the time to know where they are. They're not just low permeability zones for storage, but they're also highly reactive, and they could be causing the assimilation that we're looking for to have happen. It impacts our remediation system designs. It might behoove us to design better monitoring systems so our data that comes back from those systems is more clear cut. And I suppose ultimately we're looking to build these conceptual site models that are process-based so we can be predictive in our management decision-making. And I guess the other main point is all these processes that are happening in the subsurface have different relative importance depending on whether you're working in sands or clays or fractured sedimentary rock or crystalline rock systems. And so there is a lot of complexity for us to think about. Thank you.
Yeah. Thank you very much for the presentations here. And here, just a reminder for the audience, we have this QR code, and you can send him some questions, and Daniel will take care of that one. we later also have 2 questions for the audience. Before we go to that, I would take up some points which were made here, and what you saw is the very different scales. And the question, of course, is where do you put our resources? So do we put our resources in protection of the small-scale issues, also in terms of research and so on? Or how do we handle the large-scale deterioration of groundwater quality? And I would like to start to ask this question to Ilka.
Thanks so much, Peter. I guess, to be honest, the answer to that is it depends where you live, I guess. And you know, if you live somewhere in Southeast Asia and you're in these regions which are affected heavily by geogenic contamination, like arsenic, for instance, I think that's where the resources go. And site contamination may just be a luxury which you can't afford in those kinds of areas. I do understand, though, that if you live in urbanized, highly urbanized areas, you may have several. In your local urban area, you may have several site-specific contamination issues. They all provide cumulative effects. You will put your resource efforts into that. So I think it depends very much where you live around the globe, where you put your resources in.
Yeah. Beth, you worked a lot on contaminated sites, remediation issues. What's your perspective on that one?
Well, I guess my feeling is it actually requires both, and it requires critical thinking at multiple scales and trying to optimize how and where you do these things almost. So I think there's complementarity in working at multiple scales so that you can build in some efficiencies, cost efficiencies, so that you're not just operating blindly. You don't end up being surprised 5 or 10 or 50 years from now. Or at least that's what I see our role as a profession, to be quantitative in our approach.
Thank you. I showed you that we got more and more contaminants in groundwater, where we sometimes we are surprised. And that, of course, triggers the question, what is expected next? And Juliane is, I guess, an expert in that one. What do you think is the hot topic in 10 years or 20 years?
Unfortunately, I have no crystal ball. And I can also not name now a substance class, but I can say some about the properties. I think that we have to deal more and more with persistent and mobile compounds, which really do not degrade in the unsaturated zone, which reach the aquifer and which are mobile and go far away from their contamination source. So, and there I think we have now the analytics to deal with that, which was a bit not so much in the focus in the 20 years ago. And also we have several compounds like the PFAS also belong to this class. And maybe there is now, PFAS will be forbidden, but then there is replacement. And these replacement compounds might have really similar properties because they have to have similar function. And so we have to look out for these replacement compounds. Also, there are more pesticides registered. Fortunately, not too many, but there are new pesticides, and these are spread over large areas, and there the transformation product especially we should also look out. So I guess we will also find transformation products from pesticides and maybe from other compounds. And then, of course, it also depends very much whether we say it's a threat, whether toxicologists say it's critical. So for PFAS, for example, there was this, we knew about them in the groundwater already 10, 20 years ago, at least in Switzerland, but the threshold, the toxicity threshold was so high that we said it's not a problem. And now toxicity thresholds went down, and now we have a problem everywhere.
Yeah, thank you very much. What we also saw in the presentations is, and Juliane mentioned that we have large data sets. So we have more and more compounds, but also what Beth showed is that we need more and more data for subsurface characterization. And then, of course, the question comes up, how do we handle such large data sets, also with respect to current or future technologies like artificial intelligence and so on? And I would like to ask Beth to give her opinion about that one.
Okay. Well, following on to Juliana's comment about the future contaminants, I'm curious myself whether we've looked for those things that have been in the ground from long, long ago. Did we have the methods to find them or look in the right places, along with the detection capabilities that are needed to find them? So we may be surprised in future decades about something that happened so long ago that it's out of our mind, not so much something new that's going into the ground. And that's, I think, part of the interesting challenge. But coming to the large data sets, which is what I'm promoting here, not blindly and without bounds, but rather with critical thinking and lateral thinking brought into the mix, right? We're constantly thinking, we start with a conceptual model, we start with what are the key questions, and then we gather data to try to answer them and remove some of the competing hypotheses. So as we advance our knowledge and thinking, we can do more and more better targeted data collection. But what we've been working hard on in our field-based research group, which kind of emulate our professional practice, is to work toward methods for collecting data electronically in the field and develop workflows that ensure that it's secure and captured in a way that it's readily accessible, and move into different modeling platforms or software platforms to facilitate the data analysis and synthesis. And so it does require a focus or dedication on data capture systems and the intensity there. We actually discuss our data capture activities as part of our work plan activities, so it's kind of brought into the workflow right from the beginning. And then AI and machine learning opportunities that everyone's excited about, I think, have the potential to be put to use, further building efficiencies into future activities, I think. So that's going to take a little bit of a switch, I think, in how we do things.
Thank you very, very much. If you talk about groundwater quality for future generations, you also have to monitor the groundwater quality. And I know just a few countries worldwide who have long-term monitoring networks installed. And since Ilka showed also these large-scale issues, the question is, what are the Australians doing? And what do you think is needed in terms of groundwater monitoring on a large scale? This is important to find out trends, for example, for deterioration.
That's right, and I don't know how it is in other countries. I can only talk from the Australian perspective, and we do collect a lot of data, but it's not necessary. It's often, it's often site contamination data. It's specific data when there is an issue. We don't generally monitor for the resource as a whole to look at deterioration or at trends in resources, so we don't have a dedicated national monitoring network for water quality which looks at long-term trends, and I think that is really critically needed, at least in the Australian context, and I think we've got a question for the audience where we would like to see how the situation is in other countries.
Just before, there was already a question from the audience about also the cost of monitoring, because you saw the complexity on compounds, and it's good to ask countries about, yeah, we should have more monitoring, but who should pay that, who can afford that? The public has to pay, or is there actually also somehow the polluters that should be involved? What could be a finance model?
Go on, who should pay? Ilka, do you want to start on that one?
I guess that also, again, depends very much where which country you are in and what kind of capacity you have to pay. I mean, in Australia, I think we have the capacity to come up with a national monitoring network, which is financed. So I think there is a will and there is an ability to do it. I think we need to get perhaps better organized, or it's also that people are just starting to get more and more aware that that is actually what is needed. So in a country like Australia, I think it's definitely possible to be able to finance this, but there is also a lot of data sitting with our industry. We've got a large mining industry which has a wealth of information, a wealth of data, but we haven't got the legislation in the moment, which makes these companies have to hand over some of the data, and I think we could be more efficient because a lot of monitoring is actually being done already, but it's actually not being collected necessarily in a concise way.
Yeah, maybe also to add, we have to be strategic. So, for example, in Switzerland, we have a group which discuss what should be the next compounds to monitor in the national monitoring network. And then we have also maybe to get rid of some compounds or say, okay, we only check these every 10 years. So we have to be strategic to keep the cost, of course, low. But for the national monitoring, I think the public has to pay.
We want to pursue that a bit more general with the state of monitoring in different countries. So now you can answer questions. We want to see a bit an overview, what you think in your country. Is there sufficient groundwater monitoring going on? Quality-wise, not, or you don't know. So you have basically the three answers you can get. Do you think you have adequate monitoring long time, especially long term, not just snapshot once and that's it, but really long-term national groundwater quality network?
I would just like to add, too, that I do think it's a multi-scale approach. We have national monitoring networks that exist in some countries. In Canada, we've really highlighted municipal water supply systems owning their monitoring at the regional scale or the capture zone scale. And then individual site owners that have contamination and they're obligated to perhaps characterize for remediation purposes, they have monitoring networks as well. And so can we capitalize on those multiple scales of monitoring systems to help improve our knowledge of these systems as we move forward?
Yeah. So the result is very interesting. For me, it's a little bit unexpected, and that's probably because there are many people coming to the Swiss Day because Switzerland has a very good monitoring network, as does the state of Baden-Württemberg in southern Germany, and the Danes have a good ones in Canada and so on, but I guess in many countries it's not that well developed so far.
We can then go to the next question. We saw a wide range of issues, but we're really wondering what you see in your country as the main groundwater quality concern. If you can indicate maybe continent and concern, so Europe, nitrate, or Asia, just to see what, but we have actually from the right priorities. So we have. So if you can specify the continent before the compound, that would be interesting to see a bit just type maybe the continent before the problem.
I guess the winner is nitrate.
Agricultural
but it also depends a little bit on the country. And don't forget E. coli, for example. There's also a big issue worldwide, especially in developing countries, about groundwater safety and so on for drinking water purposes. And in Europe also, and in other countries, industrial countries, of course, the perfluorinated compounds come up. That's one important thing right now.
But it's good we don't see chlorinated solvents anymore, right?
Yes, that's...
20 years ago, maybe there would be another answer here.
But I don't think it's because they're not in the aquifers. It's because we know how to treat them. So they're there.
Exactly.
They're not, they haven't gone away.
So we don't get excited about them anymore because we have a clear plan how to manage these type of sites.
Engineer controls.
So after all these concerns, I would like to come to some final statements here from the panelists, and this is about giving us our view, optimistic vision for preserving groundwater quality for future generation. And maybe I start with Beth.
There's so many things.
Already started it.
Yeah, no, I guess what comes to the top for me is that I live in the space of research and the state of the science and technology, and yet I guess when I get discouraged, I see this big gap or lag between the state of the science and technology compared to the state of the practice. And so we have so much potential that's not being put to use, and it's not because those state of the science techniques are expensive. We just need to learn to use them and how to put them to use cost effectively. So that's my optimism, is we have so much potential to do a better job. And I think that'll spill into better communications with policymakers and better communications with the public, that in fact we do know what we're doing and we do know how to make decisions based on risk and priority.
Thanks. Ika.
Yes, I'm positive about the future. I think, we do learn from our mistakes, I think. We are getting better at handling contamination. Just now, hydrocarbons, for instance, they weren't even on the list anymore, not because they're not there, but people aren't as concerned anymore because we have a handle on what to do with them, how to remediate. So I think we do learn, and we are getting better at it. So I think I'm not concerned as such. What I would love to see, and maybe that's just from the background I come from, is just really a bit more emphasis into long-term monitoring and including redox state of aquifers, major minor ions, not only site contaminants, to get a better handle of water quality as a whole of the resource. And I'm from a modeling background. I'm a geochemical modeler, reactive transport modeler, and a lot of emphasis is currently on modeling, I feel, and what we actually need, I think, to make models better, to predict contamination, is really good data, long-term data sets, and that's what I would like to see, that we put a bit of emphasis into the monitoring.
Yeah, thank you. Juliane, you're optimistic of finding new compounds?
I think there's a lot of awareness. So chemicals are now seen as a threat next to biodiversity, next to climate change. And there is also science policy panel now under UNEP established, which kind of want to address this problem. There is also now regulation, slowly but coming, that mobility is another hazard criterion in the registration in the EU. So there is awareness and there is interest to improve regulation, which then hopefully finally, also with circular economy, that we hopefully bring less chemicals into environment on the long run.
Thank you very much. And since we have the Swiss Day today, I ask Daniel about his optimistic view from the Swiss perspective, maybe.
Yeah, no, I think like in other countries, we really want to also in the future have the possibility to pump and drink without treatment. And I think there's a few things for optimism. Like, I mean, we saw with Juliane, we have like hundreds of thousands chemicals, and in a way we can be lucky they're not. We can say there's relatively few really widespread in groundwater. There might still be surprises, but that also shows for many chemicals already what the actions are taken are working, or the aquifer, there's still some filtration. So it's actually not everything breaks through. And then the other kind of optimism is also for those that break through with all the knowledge we gathered in the community in the last 50 years. We know why, and we understand why. We had a little bit of discussion whether we really can extrapolate from the knowledge right away to new compounds or not, but we have a good understanding what the problem is, and we have taken steps. Peter showed very nicely the time scales. We learned about these long time scales, and I mean, we address a lot the point sources because we see the time scale. We cannot wait it out, and there's a lot, I mean, especially in Switzerland, the remediation being done, addressing this problem. But then I think this was discussed here, the more diffuse sources, and we saw it also popping up, nitrate keeps coming up. There's even more persistent issues, and here there's some more steps being needed really, because there are also long time scales there, like Peter shown, and there comes really the point we haven't really approached that much, the regulation. How should we update regulation in the face of these new challenges? And I think the preventive approach is the only way to go, that we really think more about how we can prevent substances going in there with land use patterns, something we're doing, trying hopefully successfully to implement in Switzerland. And so if we then address these critical substances that we know, in time I think we can have also good water for future generations. Okay.
Yeah. Thank you. I guess that ends our panel discussion here. I would like to thank the panelists and of course the organizer for having us here. Thank you very much.
Thank you. Thank you also for coming from all around the world, Australia, Canada, Dübendorf. So before you walk out, this is always meant with these panels to kick off the discussion. We clearly didn't answer all the questions, so we have now some events for people that want to go into an in-depth discussion, to go to the smaller rooms. In terms of water quality, we have a session on agriculture and water quality that starts at 10 o'clock in R4, then there's a PFAS session in the afternoon. And there we have a lot of short presentations, but in the afternoon we have also a global debate in a smaller group from 2:30 to 3:30, how different countries address the problem of persistent mobile contaminants. And so hopefully a lot of people come from different places and say, what is in my country the issue and what is the policies that are currently in place and what policies might be needed to address that. So this is in R6 then in the afternoon. And as Juliane mentioned, we have this unique opportunity to have this mobile mass spec in front of the entry. So there's tours there, don't miss that. This is really an LCMS that you can take anywhere. So if you want to learn more about that, please go there. And just maybe to point out, in the afternoon, the focus topic is safeguarding the multifunctional underground with CO2 storage and so on. And there's going to be the lunchtime lecture already on that before the plenary. Don't miss that as well. So I wish you a good day and make a good choice of among the many activities. It's a dilemma where to go from now. It continues at 10 o'clock in the small rooms.